please.
这个要求有点怪。
要变去了。
昨天上一个的主席讲。
确认他们有
可是我是不同的主持
对啊，所以上面没有，所以
到时候他们只准备一个题目，
跟确认。
这样你这样有点怪啊。
那是确认，因为昨天那个就有通知我们的队说，就是叫我们直接确认他们有人停止，因为他们如果再 reject 下去，要分数对，就是昨天赛事方有跟我们讲。
你是负责同学吗？
对。
好吧，那你们可以同意吗？他们只能讲一讲。第几号？
对，我们昨天就有被通知的。
哪一笔？14年。
对，
他们只能14年，对吗？等一下那个时间，你应该早点跟我说，我不知道。Okay, please.
We would like to challenge problem number 14, looping pendulum.
And of course you accept, right?
Okay.
Everyone, please write down your information on blackboard, please. Oh
他们选这边以外的。
不是那个，上面有关知道吗？
Okay, report, we have 5 minutes of preparation. And the representative of our reporter is Zhang Yexi. From the opponent is Sun Jiaxi. And then reviewer is Huang Shaoxi.
我
topic to be discussed is number 14, looping hand rule. If you are ready, you can stop earlier. Okay, reporter, please.
Good morning, everyone. Today I'm going to show you how we can looping and reveal problems. Public distribution is connected to the one heavy and one light. There with a string over horizontal rod and lift out the heavy load by holding down the light one. Release the light load and swing around the rod, keeping the heavy load from falling to the ground. Investigate the ground. We build our setup like this. First, we use we put the heavy load through and use the string tool, and we will hold the string there and use this to make sure the angle and the theory is by law of conservation of mechanical energy. It's easy for us to find out that the relationship between a light load and a heavy load are major influenced by the angle. The angle means how we hold a string and when we hold a light load, it will have angle. The string will have an angle, right? So we use two factors to do the experience. One is the weight between the two, the weight of the two loads. Second is the angle. In the beginning, I hold a rope so that the tension is equal to the heavy load weight. After loosening the hand, the rope tension becomes less, so the force is not only bigger, but also the speed is getting higher too. So the tension is by the way, the tension was then given a force. The force is bigger than the gravity of light loads, but bigger than heavy loads. Because the heavy load fall in the heavy load lifts, so also do a circular motion. But at least they will do a circular motion. So at first, when we get a string, when we get an angle of the string getting higher, and the speed, the speed in the first moment will getting higher. So it's directly influenced by the first how we do the experiment in the first angle. So the string will the string after they do the after they may use a record. This is our experiment. So the first will be like this, right? So it will do the motion like this. After it touch to this line, it will do a circular motion that's a circle around the stick inside. So the next page. Next page. This is our data. This is our parameter. We can see that it's when the angle getting higher and the circular motion is doing more clearly. So this is how we use in our experiments. Next. This is our conclusion. Thank you, everyone.
Okay. Conan?
Thank you, reporter. Would you turn to page 3, the theory part? And could you explain what do you mean by the habit of falling and the habit of lift?
Oh, that means the habit of, so after we put out this flat and this tension and we can surely like this. We can symbolize this to this. So when after we don't give it the force, we will up because of these two the different heavy. So we will fall. And
Do you mean that the habit of lift and falling?
the heavy will fall in and light will lift.
The light will lift and the habit of will fall.
Sorry, I pressed wrong.
Okay, that's okay.
Let me make sure.
In your theory, you said that you think the most important parameter is the weight of the two logs and the angle, right?
Yes.
And what do you think that when the mass ratio of the two logs is getting bigger, what would the outcome be like?
You mean how the weight influences?
Yes.
I can surely, I can, when we do the experiment, we found that if the weight is not heavy enough, we'll have to run in heaven. One is
You
just,
mean the habit of is not heavy enough?
Yeah.
Both of them.
I mean, if this is N and this is N, and I mean this.
Oh, okay. So you mean the mass ratio is big enough so that the motion will rotate, right?
Yes. If this is not big enough, the line will make you like this.
Thank you.
Stop. Conan, please prepare. Okay.
Hello, jury and fellow debaters. I'm the opponent of Phoenix Excelsior, and today I'm proposing the question number 13, looping pendulum. First of all, it's the problem statement. The problem statement told us that connecting load when heavy on one line with a string over a horizontal rod and lift up the heavy load by pulling down the lifeline, and release the light load, and it will swivel around the rod, keeping the heavy load from falling to the ground, and investigate this phenomenon. And next is the reporter's outline. First of all, he gave us his experiment system as observation, and he did a good job on give us a clear picture. And during his presentation, there are some page number that's wrong that might confuse the rest of us. And the third part, he told us about the conservation of mechanical energy. And I think his theory is a little bit too brief to explain the phenomenon, the experiment, and conclusion. And in the experiment part, he told us about his setup, and he thinks that the releasing angle and different balls will influence this phenomenon. But I think he's a little bit lack of parameters that he could have improved. And in conclusion part is that he told us about when the releasing angle increases, the velocity of the light load will increases too. But I think he could have improved that of his time control. And this is the structure of solving problems. The opponent thinks that first of all we have to find out the mechanism of the pendulum and how it works, like how the friction influences this whole system and different phases of the motion. And next is the operation of the experiments and technical problems like collision and release device that the problem will face during conducting the experiment. And lastly, the important parameters that affect the motion of the two logs. And this is my points of discussion. First of all, I would like to ask the reporter about the main factor of this phenomenon. And next, I would like to discuss with him the static friction and the kinetic friction, the transition between them. And third one is the measurement of the friction coefficient which the opponent think is an important factor. And lastly is the force analysis. And during the experiment part, I would like to discuss with the reporter about his setup, like how he designed his experiment, and the releasing device, and what if the collision happened. And last is the result. Result is about I would like to discuss with the other parameters like prediction of other releasing angle and the length of the string and material of the string and what would the friction influence the result and the mass ratio between the two rods and the radius of the rod. Like other parameters, how the prediction that how would the outcome be like. And I would like to skip to the next phase.
Okay, please.
Okay. Since you measure two loads and a string, could you explain like how did you design your setup?
How I will
Yeah.
do the setup.
Yes. Can you this for us?
First we do finish and we finish and use the angle here.
Chair, may I use the block?
Yes, please.
Thank you. And also, I want to make sure that when your rod is here, you put your heavy load here or put it here
So we put on the top.
on the top of it. So there's no distance between the rod and the heavy load, right?
Yeah.
Yes. And the releasing angle means that the angle release. You mean this or this?
The library here.
If the light load is here in this one,
Yeah.
okay. Did you observe the phenomenon like when the light load it accelerates downward when it hits this string?
Yeah, so we met, the phenomenon happened because of this phenomenon happened,
So the collision will happen, right?
Yes, we have ruler angle video.
Okay. Then could you I would like to first ask you what do you think? Do you think the friction affect a lot in this phenomenon? The friction between the rod and the string, because this is do you think the friction influence a lot?
The friction influence a lot, especially the.
So you did think the friction influence a lot, right?
Yes.
And since the friction influenced a lot, could you show me how to measure your friction coefficient? Like, how did you measure your mu k and mu s between the string and the rod? Could you show me? So you didn't. Did you measure your kinetic friction and static friction? Did you measure it? Did the recorder measure it? This means the friction coefficient between the string and the rod. Did you the friction coefficient between the string and the rod? Did you measure it? Okay. I disagree with the reporter that he didn't measure the friction coefficient between the string and the rod, since I think it's the main factor affecting this phenomenon. And I think this is the part that he could improve. And I think you should I think you could use an output machine to measure the kinetic friction and use a Capstan equation to measure the static friction. And do you know what exactly output machine can measure the kinetic friction? Output machine. It's like so you conducted this kind of experiment like this, right? Yes. And output machine is like this when heavy load and the light load. It will have the same acceleration, so you can measure your kinetic friction. Yes. You did use it. You didn't use it. Okay, that's okay. I think this is a part that you could improve. And you did the experiment like the releasing angle of the light load, right? Then what do you think that you did think that when the releasing angle is getting higher, the light load will accelerate downward faster, right?
Yeah, in fact, the experiment we just actually
You just did the 90-degree.
Yeah, so I think we should the choice is under 90 on the time.
So you only did the experiment like in
Yeah.
this. Okay, and what do you think that if the angle is up right here, what would the phenomenon be like?
my point, I think because power, if we put a power here into the power line, so
Yes.
I think if we getting higher, the speed will getting the first speed of
You meant the light bulbs.
that is your falling and hit and is touched by the potential.
Okay, then may I ask about did you observe the angular velocity of the light load or angular acceleration of the light load? What did you did you measure the angular acceleration of the light load or angular velocity of the light load? That's okay. In your presentation, you said that you observed the angular velocity, and I disagree with the report that I think observing the angular acceleration is the right way to observe this phenomenon. And could you tell me that when you didn't do the experiment, and can you predict that if the length of the string is getting longer, then what would the phenomenon be like? Yeah, different length of the string. What would the phenomenon be like?
My point, I think the thing, this field is getting more higher, so I think
what do you think that if the mass ratio, like the heavy load is heavier and the light load didn't change, what would the phenomenon be like?
10 to the page. 10 to our data.
Yes.
We do experiment. The number up is means the.
Okay. Thank you. And could you tell me what the force analysis you did in the experiment? Like force analysis, like which force given the thing to rotate, the force analysis. Like you got your rod like this. This is your rod, right? And you put your light load here up here. This is your light load, and this is your rod. And you did put your heavy load like this, right? And can you tell me what your force analysis is like? Force analysis, like the force. Could you draw the force for us? Like what? Okay. Yeah. What will the string tension be? Where will the string tension be? String tension. This? Oh, okay. So you think the string tension will be like this? And you will put it and then.
The rotation of the table and the first year is smaller than the first year.
Oh, okay, thank you. And I talked about a main factor with the reporter that I reached to a consistency that we both think the friction influenced the phenomenon alike. But however, according to his lack of parameters, we did predict some of the result and other parameters like cos-like. We talked about the string tension and the force analysis, and I also did let him predict the length. What if the length of the string is getting longer, or if the mass ratio is getting bigger, what will the phenomenon be like? And I think that he could improve on since he also thinks that the friction influenced the phenomenon a lot. I think he could improve on he could measure the kinetic friction and the static friction coefficient between the horizontal rod and the string. I think this is the part that the reporter could improve. And thank you.
Okay. Reviewer, you have 3 minutes to ask questions.
First, to ask the reporter, how do you think the friction will affect the tension?
How the
Friction affect the tension of the rope.
how to
There must be a friction. And how does it affect the tension of the rope? Okay, thank you. And opponent, what's your opinion that when the light load rise the angle of the light load and what the effect of this phenomenon?
When the releasing point is getting higher,
Yes.
I think the light load will accelerate faster. That means that the acceleration of the light load will be faster.
So did you think if you want to stop the heavy load faster, you need to put it on a higher angle?
Yes.
And reporter, what's your opinion?
in fact, if we want to speed the heavy load,
Report, please speak face to us.
okay.
So we can hear.
I think that if we want to stop the heavy load quickly, we need to keep a big angle because the speed will be higher.
Okay, thank you. And opponent, what's your opinion that the friction affects the tension?
I think the friction is main factor because there has to be friction between the string and the rod so that the heavy load will stop. I think this is the point.
So did you think we can calculate that friction?
Yes.
And what's your opinion? Can we calculate that?
I think we can calculate that, but we can.
Okay, thank you. And here's another question for a reporter. Did you think the change of the friction coefficient will affect the phenomenon? The change of the friction coefficient, you use a different material of the rod of the.
I think
Well, so how does it affect?
if the friction that goes through the rod between the rod and the string getting higher, I think the light will quicker. We will do more
Circular.
motion until the end.
Okay, so you think it's a circular motion?
At the end, but after and it's
Okay, thank you.
还是啊。
Okay, I'm done with my preparation.
Okay.
And hello everyone, I'm Hong Shaoqi from Lindau High School of MDH's A team. And today I'm talking about the review of a problem 14, looping pendulum. And here's the problem statement. The main point is one heavy load and one light load, and keeping the heavy load from falling to the ground. And here's the overview of the reporter. They have an obvious and easy experiment, which I think is good. And they have an obvious chart of the result of the experiment like that. But here's some of my suggestions. You can try to figure out the relation between tension and friction. And you can put your picture on PPT instead of drawing on the blackboard when you are reporting. And are there any functions that fit your result? You didn't make your result into a graphic. Maybe you can make into a graphic and find some functions to fit inside the result. And are there more parameters that you can do in your experiment? And here's my opinion. I think the difference between the tension both sides is the friction. Overview of opponent. Advantage. You have nice attitude to the reporter. And you have a short question on the parameters of his experiment. And here are some of my suggestions. You can speak more clearly. And what's your opinion to the problem? Although you try to lead the reporter to figure out more of this phenomenon, but you didn't talk about your own opinion. So what I want to know is your opinion. And discussion 1. The opponent asks what's the main factor to a phenomenon. And the reporter did think the friction affected a lot, but they didn't measure the friction. And the opponent asks, can you analyze the force? And the reporter draw a picture of the force, but the direction of the tension was wrong at first. And I agree the friction did affect a lot. And here is second discussion. Opponent asks, how do reporter design the setup? And where is the heavy load? And will the light load hit the heavy one? And the reporter draw a picture on the blackboard. But I think the reporter didn't answer the third question very well. He didn't talk about how he avoid the hitting of the light load and heavy load. And I think here the opponent do very well on trying to leading the reporter to figure out more about this phenomenon. And discussion 3. Opponent asks, the rise of the initial angle, what will affect on this phenomenon? And the reporter says, the initial velocity rise, but I don't think so. The initial velocity will always be 0 because you hold it on your hand and release it. And I asked the opponent that, what do you think of the rise of the initial angle? And I think her answer is very correct. And here's all of my review. Thank you.
Okay. Reporter?
In the end, I think our opponent didn't consider I think our experiment didn't explain the friction to mind. That is how we can do it more in this experiment. Thanks.
Are we done? Okay. So that concludes this session. I leave jury for 1 minute for doing calculation of your scores. Oh, you can ask questions. Sorry. Jury, please ask questions now. Yes, please.
I have a question to the opponent. What's your solutions to the hit of the swing?
The horizontal rod is here, and we actually put the heavy load here, and the light load is right here, right? When the light load hits the string, we will put the heavy load a little bit to the right, and make sure every distance is the same. Yes.
Thank you.
Other questions from jury? I have a question for the reviewer. Yes. Could you on the blackboard draw the force diagrams of the string?
of the string.
Yes.
And the difference between the both side tension will be the friction.
Yeah, but what about the direction of the rod on the string?
Direction,
The rod, I think, also applies some forces on the string.
yes, friction, of course.
Which directions? Opponent, do you agree with his diagrams?
No. Can I draw my
Yes, please.
I think when the
You can draw a new one, for example.
Oh, that's okay. When the string gets down, the force will be like this and keep the heavy load still. So I think the friction is the opposite way of the relative movement between the string and the rod.
What about force on the rod to the string? From the rod to the string.
From the rod to the string, it will be force on the rod. The force on the rod to the string, it
Yes.
will be the friction.
Okay.
Can I draw another clear one?
Okay.
If this is the rod and
Okay.
this is the rope, and if we design the very little angle of and in the static equilibrium, we can consider the friction in this side. But this phenomenon isn't exist in a static equilibrium. But if we ignore the mass of the rope, we can still use the result that we get in the static equilibrium. And the normal force will be the with the very little piece of the rope.
Which direction?
Normal force.
Yes. Okay. Thank you. Reporter, do you agree with their diagrams? Okay. Other question from the jury? Okay, if no, then I'll leave the jury for doing calculation of the scores. Thank you. The juries are fine? Okay. So we'll start from the reporter.
Photo 是给那个气氛更好，照的。
Please face toward that direction. Okay. For the reporter, 6, 4, 4, 4. And next, for the opponent, 8, 8, 7, 8, 8. Finally, for the reviewer, 8, 7, 7, 7, 7. Okay, so we conclude the first fight. Now is 20 minutes after 9, so we'll resume after 15 minutes. Please come back at 35 after 9 o'clock. And all teams, please switch your seats. And make sure your laptop connects to the screen smoothly.
For the ball to float. So this is my presentation outline. So first, for the observation part, I'll show you 3 kinds of observation video, which we use 3 kinds of funnel to investigate this phenomenon. And for the theory part, we'll explain why this phenomenon works and give you a final formula for this phenomenon. And for the experiment part, we have 3 parameters, which is the shape of the funnel and the weight of the ball, and also the gap in the funnel. And so finally, we got some conclusion for this phenomenon. So this is my first observation video, which we use a regular funnel to do this. And this funnel is a conical shaped funnel. So as you can see in the video, the ball shake and rotate in the funnel, which means that the ball is very unstable in this system. So the second observation video is we use spherical shaped funnel to do this experiment. And as you can see in the video, the ball didn't shake as much as it does in the conical shaped funnel, but it still rotates. And so this is the last observation video we do. And the funnel in it is the spherical shaped funnel, but there's baffle in it. So as you can see in the video, the ball didn't rotate and didn't shake, which means that it's very stable in the system. So then we'll move on to our theoretical model. So we first assume that the rho won't change in our experiment, which means that rho is the air density, and the atmospheric pressure will equal to 1 atm. And so according to the continuity equation, AF, which is the area which the airflow goes through it, will equals to this formula. And so according to continuity equation, we can get the velocity through the funnel will equals to the volume of the air over AF multiplied delta T. And then according to Bernoulli's principle, we can get that the atmospheric the pressure which caused by the airflow will equals to the atmospheric pressure minus half of rho squared V. And then we can get what we get in the former page of V into the formula, and then we can get the pressure which caused by the airflow will equals to this formula. And then as you can see in the picture, the force caused by the atmospheric pressure will equals to the weight of the ball plus the force caused by the pressure and plus the impact force and plus the friction. And then the impact force will equals to this formula. And then for the force which caused by P, which is F1, the reason why we integrate it from theta 0 to half of pi is because that we can't include the area which affected by the impact force in it. And so we replace F to PA, and we put what we get with for P in the former page in this formula, and then we can get F1 will be like this. And then for the using the same way, we can get F2 will be like this. And the reason why we didn't integrate it from theta 0 to half of pi is because that there's no impact force under the ball. And so then we can get our final formula will be like this. And so if there is baffle, which is like here, to avoid the impact force, then the rho over A0 will equals to 0 because there is no impact force. And then to simplify this formula, so we let B to be this formula and E will be this formula, so that you can see the weight of the ball will have the positive correlation with the square of the flow rate. And to move on to the conical shaped funnel, for the conical shaped funnel, the delta H will not be constant. So this is the formula we get for delta H. And so this is my experiment equipment. So first is the airflow-meter, which we use to measure the flow rate. And the throttle is for controlling the volume of the air, which go through the pipe. And nails is for changing the weight of the ball. And then the air compressor is for blowing out the air to go through the pipe. And we choose to use styrofoam ball, which is easier for us to add the weight. And for the funnel, we have three kinds of funnel, which is the conical shaped funnel, and the spherical shaped funnel, and the spherical shaped funnel, which have baffle in it. And this is my experiment setup. And so in order to make it more clear, I'll draw it like this. And so first, we open the air compressor, and we first let the ball float in the funnel. And then we'll slowly close down the throttle and until the ball flow, and then we'll measure the airflow meter. We'll measure the airflow rate from the airflow meter. And so this is my experiment parameters. So first is the different shape of the funnel and the back of the funnel, and also the weight of the ball. So this is the first experiment we've done, which is a different shape of the funnel. And this is the control variables we have. And what we change is the shape of the funnel, which is the conical shaped funnel and the spherical shaped funnel. And so this is the chart of the conical shaped funnel. So as you can see, the tendency of it fits in our theories, which if the weight of the ball increases, then the minimum flow rate it needs will also increase too. And so the reason why these spots is not on the theory line is because that if the weight of the ball is too light, then it will be unstable. So the minimum flow rate for it to float will increase. And so this is the chart of the spherical shaped funnel. And so the tendency of it is also fit in our theory, which if the weight of the ball increase, then the flow rate it needs to flow to increase too. So this is the comparison of two kinds of shape of funnel. So as you can see in these two charts, the dots for the spherical shape funnel is more closer to the theory line, which the conical shape funnel is more further. So we think that the spherical shape funnel is better than the conical shape funnel. And the reason why this will happen is because we summarize this because the spherical shape funnel, the shape of it is more closer than a ball. So so that if we use conical shape funnel, the ball will hit the wall of the funnel, and then it will be unstable. And so the second experiment we've done is a gap in the funnel. So how we make the spherical shape funnel is that this is a gashapon case. And so we dig the gashapon case, we dig a hole on it, and we stick the pipe on it. And so the funnel is done. And we add baffle in it, which we stick the baffle under the pipe, and then we can control the distance between the pipe and the baffle. And so these are the control variables we have, and this is the parameter which we've changed, which is a gap in the funnel where from 0.1 centimeter to 1 centimeter. So this is a chart of the gap in the funnel. So the reason why this looks not very pretty is because we stick the baffle from our hand, so it is not very precise. But the tendency of it is correct, which is because that if the funnel gap increases, the minimum flow rate for it to flow will increase too. So this is the next experiment we've done, which is the weight of the ball. And the funnel with gap, which is because that for this funnel, the ball in it will be more stable because there is no impact force. And these are the weights we've changed. And so this is the chart for changing the weight of the ball. So because we use the funnel which has gap in it, so it is more stable. So the data will be on the theory line. And so for the conclusion, I'll explain the reason why this phenomenon will happen. It's because that according to Bernoulli's principle, the velocity which go through the funnel will be bigger than the velocity which go out from the funnel. And so the pressure which caused by the airflow will be smaller than the atmospheric pressure. So the ball will float in it. And this is a conclusion of the first parameters. So from these two charts, we can see that the spherical shaped funnel is better than the conical shaped funnel. It's because that the spherical shaped funnel shape is more closer than the ball. And so this is a conclusion for the second parameter we've done. And so the tendency of it is fitting up theory, which is if the funnel gap increase, then the flow rate needs to flow rate increase too. And so for the conclusion for changing the weight, because we use the funnel which has baffle in it for it is more stable in the system. So if the weight of the ball increase and the flow rate, it needs to flow rate increase too. And the weight of the ball has a positive correlation to the square of the flow rate. Thank you.
Okay, opponent, please ask questions.
Okay, I have some questions. Can you explain again what is the gap between the funnel?
Can you go backward?
Yes, please.
So this is the funnel, and we stick a baffle in this. So this is the gap.
Oh. So your delta H is the wind blow out this space between this, and instead of the ball between this and this, which is your delta H, this and this.
Which funnel do you mean?
You said delta H is the row and the funnel's distance, or your balls and the funnel's distance.
For the conical shape funnel, the delta H is the distance between the funnel wall and the ball. And we know that the delta H will not be constant, so we choose to integrate it in our formula.
Now why do you write this delta?
And this is a funnel which we have baffle in it. So for this case, the delta H from here to here will be the same.
So there shouldn't be out. Okay. And this is also.
Yeah.
Okay, and I want to ask to your experiment video 2 and 3. Oh yes, please and next. What's different between these two?
I've just explained in my presentation that the first video.
Time's up. Sorry. Opponent, you have 3 minutes to prepare. Okay, please start. Tony?
Okay. Hi everyone, my name is Wu Honglu from MDHS18. Today I'm going to opponent the problem number 4, Bruno and Ball. And this is the problem statement. And there's the summary of the reporter. The use theory is Bernoulli's equation and continuous equation. And their experiment, they have ball, paper, funnel, cone, and some nails to add the mass. Yes, and their parameters will be is the ball weight and the shape of the cone and the gap in the funnel. And here is some advantage for reporters. First, she speak clearly and the PowerPoints look very good. But our suggestion for your data is you didn't draw the error bars in your data. And this is the setup and theory and experimental data for reporter. First, they have good picture to introduce their phenomenon. And they did very many experiments, so they have many data. And their theory is very detailed. And the experiment data, it seems like it very matches the theoretical curve. But I think they can consider more parameter like the different material of the ball or material of the cone. Yes, and let's go to our discussion. First, I want to ask, did the ball rotate in your theory, in your experiment?
Observationally. This one will rotate because this will rotate too, because there's no backfall. So the impact force will hit the ball directly, so it will cause a rotation.
Oh, so it will rotate.
Yes.
Okay, then I want to ask your theory. Can you explain this phenomenon totally by the Bernoulli's law and continuous equation to your theory?
So I've just explained it.
Can you? Because in the Bernoulli's laws, the fluid shouldn't be pressed, right?
Compressible?
Yes, compressible.
So we've found some information on the NASA's website. So if the float Mach number is smaller than 1, then the float can be considered as the incompressible float.
Also, if the speed is high enough, you can consider it as uncompressible.
Low enough.
Low enough.
Yes.
Okay, but in your theory, you did write the delta V, right?
That is the volume of the air, not the velocity.
Oh yeah, so I mean the air shouldn't be compressed,
Yes.
but in the Bernoulli's law. But you did write delta V in your theory, right?
But delta V is not.
It's the volume.
Yes.
Yes, but in Bernoulli's law, the volume of the fluid couldn't be changed, right? Because
Yes. But we still need to calculate how much volume which goes through the pipe, or we can use this principle.
yeah, so I think the volume change is one of the error in your experiment. Do you agree?
But the air we use is still incompressible fluid.
Is compressible fluid.
Incompressible, because the velocity is not high enough. As we calculate, if the Mach number is 1, then the flow rate should be like this, but the flow rate we just measured is approximately like 0 to 100. So it will not be high like this. So it is incompressible fluid. So we can use Bernoulli's principle.
And what your ability to the theory is your theory part. Here, you write delta V divided by delta T. So what is your assumption about the volume? Is it incompressible or compressible?
Incompressible.
Incompressible. So why is the delta V okay?
The volume of the air won't change. Well, the volume of the air is the volume which goes through the pipe. So delta V won't change if the volume of the air.
So your delta V is this part of air.
The volume goes through the pipe.
Yeah, and what? So where the air will be deformed, will be compressed. Or not.
The fluid is incompressible fluid, so it will not be compressed. There's no compressibility for the air.
So the air's volume can't be changed.
Yes.
Oh, okay, but I think you write volume of the air delta. Yeah. Okay. Second question. In Bernoulli's law, you should discuss a string of the fluid, right? A string of the fluid. A string. Yeah. String. Yeah. It means this is a string.
Yes.
Yes, but in this condition, here isn't it's like this, and here is the ball. Yeah, so this isn't a string. So do you think it will affect your result?
No.
No?
No.
But Bernoulli's law should be used in a string of a fluid.
But the air just goes through it. But this yes, this is a string of the fluid. So, but Bernoulli's principle still can be used in this case.
All right. And due to Bernoulli's law, okay. I want to ask you first. Do you think the cross area of this gap around is and here the cross area which is bigger? You know what I mean?
Yes.
Yeah. So which is bigger?
Which is bigger?
Yes.
It
Which
depends
area?
on what funnel we use, but in our case, this area will be bigger.
This will be bigger.
Yes.
Okay. And due to the equation, continuous equation, so the velocity of the air here should be faster.
Yes.
Okay. Then do you think this different velocity will have a pressure difference because of the Bernoulli's law?
So pressure different.
Yeah.
We just didn't consider the velocity which go from the we just didn't consider the pressure which comes from out from the pipe. We just consider the pressure which caused by the airflow which goes through the body.
You mean you didn't consider the pressure here
Because
out of the pipe?
yes. No, the velocity goes through here is v0, and the velocity goes through the ball is v. So if here's a0, and the cross section area for here we see this as af.
your velocity here, right?
Yes.
Okay. Okay, and I want to ask your equipment about your setup. Is your air compressor maintain a stable flow?
Yes.
Stable velocity of air.
Yes.
Then why do you think the ball will shake in here? Why it will shake?
The ball shake is only for the conical shape funnel.
Okay. And why?
Because if this is a spherical shape funnel and this is a conical shape funnel, so if the ball is in this system, then the ball will hit the wall. If it is slow, then it will hit the wall, so it will shake. But in this case, the ball is circle and the
I
shape
want
is
to
circle.
discuss this situation. Do you think the hit will affect your results?
Yes, it will be unstable.
Also, you consider it in your equation?
Yes.
Did you?
No.
No?
No.
Okay, so I think this is one part of error in your experiment. Do you agree?
For in this case, although if the ball is light, it will be unstable, which the flow rate will increase. But if the weight of this ball is heavier, then this system will be stable.
Will be stable means it won't shake or
Won't shake a lot.
won't shake a lot.
Yes.
It's time. Sorry.
Okay, I want to ask, how do you measure you don't measure the velocity, you calculate it, right? You use your formula to calculate the velocity of the air, right?
Yes.
Okay, how do you draw your theoretical line here? How do you draw? Because I think your formula is very difficult. So how do you draw the line? Draw the theoretical line.
We can measure. We will see that the atmospheric pressure will equal to 1 atm, and we can measure the radius of the ball, and we can measure the delta H. And so all of the constant in this formula, we can measure it, so we can draw the theoretical line.
So you have some data in your
Yes.
equation.
Yes.
Okay. Final question. Can you go to your data? Okay. Through your every data, I found if the weight is very light, your error will be bigger. What do you think?
Just as that I mentioned, if the weight is not heavier enough, then the flow rate will increase because it is unstable. Well, it will hit the wall of the funnel.
Okay. How about the different kind of code?
Hands up.
Time's up.
That's very. Now I want to do my conclusion about this report. During this discussion, we talk about the shape will affect the ball's motion, and they use very many equations, so they can calculate every parameter in their equation. Okay, and in their experiment, sorry. And we have clarified that if the ball's weight is light, the shape of the ball is little, so it's very big. So it may influence the data in the experiment. And there's still something we don't realize is the volume of the air. Is it compressible or incompressible? And this is my conclusion.
Pretty good.
So is there any limit to like how like how like how heavy it is? If I use a steel ball or will it be
If the ball is too heavier, then the funnel might can't suck up the ball. So
carry some limit?
yes, but the limit of each of the funnel is different.
And then how which grade of the funnel is the best to discuss this phenomenon?
We think that it is a funnel which is a spherical shaped funnel and it has baffle in it, which can avoid the impact force.
Thank you. How do you think about their experiment?
Oh, I think this experiment is very difficult because it looks so unstable, but they did very good job on the equation and analysis. So although it may have some error, but I think it's okay.
Can you talk about the arrow?
I talk about error. First, the error may come from the collision between the ball and the wall. And second, the error may come from the rotation of the ball, because if the ball rotates, that means not every part of the ball have the same pressure. Yeah, so it's an unstable state, so it's very hard to analyze it and investigate.
Thank you.
Okay. Are you done?
Yeah.
Okay.
Thank you.
So be prepared for the final result talk. Okay. Review, please.
Hello everyone. As a reviewer of the evening guarantee, so I'm going to review the conclusion. I think this discussion, and I think the discussion is good. I discussed some this phenomenon deeply. Yes, the reporter's experiment is very complete. Their setup is very good. And the opponent's question is yes, deeply. So yeah, their reporters did have most of the think most of it is fit with the formula, so. I think this is a good discussion, thank you.
Okay. So please stand up and jury may ask questions. Oh, right, sorry. Reporter, please conclude.
So I'm going to get the concluding remark. The reason why this phenomenon happens is because according to Bernoulli's principle, the velocity through the funnel will be bigger than the velocity which goes out of the funnel. So the atmospheric pressure will be bigger than the pressure inside the funnel. So the ball will float in it. And so through our experiment, we found that the funnel with backflow will be more stable, which is because that the impact force is being avoided. And so we found that if there's no backflow in the funnel, then the ball will rotate inside. And the reason why we use Bernoulli's principle is because that we found out that if the Mach number of the field is smaller than 1, then the field can be considered as an incompressible field. And if we use conical shaped funnel, which is a regular shaped funnel, the ball will hit the wall of the funnel, and then it will be stable, and then the flow rate it needs will be bigger. And if the ball is heavier, then the funnel and the ball, which is in the funnel, will be more stable. And I had to clarify is that the error bar exists in our system and in our chart, but the error bar is too small, which is our experiment is precise, so it can be seen by our eyes. And the limitation of the weight of the ball is different in each of the funnel, which depends on the air compressor. If the air compressor flow rate is big, then the weight of the ball it can float in the funnel will increase too. Thank you.
Okay. Question from the jury. Yes.
I have a question for the reporter. I'm just wondering, when you do your experiment, vary the weight of the ball. Yes.
Yes.
And also you have a parameter gap of the furnace, and where is given in your equation. The delta H.
Yes.
Yeah, right, the delta H. And why do you think that the delta H will affect your experiment? Why?
Because the delta H of each of the funnel is different, so after we integrate it, the constant will be different. So it will affect our results.
Okay, so for the component and do you think about the delta H, because you asked about it this question, right?
Yes.
And then for your own experiment, and have you ever considered this one, the gap?
Have an error.
I mean the gap. You ever considered this parameter in your experiment?
Well, I think it's very important too, because if you want
I mean in your experiment.
Yeah.
You also did this experiment, right?
Yeah.
Have you ever considered this parameter?
Yes.
Yes. Then why did you ask?
No, I'm confusing about what is the delta H. So I asked what is the delta H means, and after they explain it to me, I know what is the delta H is.
There's a question?
Yeah, two questions to the reporter. You monitor the airflow all the time in real-time patient, did you monitor the airflow throughout the experiment?
You mean the flow rate?
Flow rate.
Yes.
You do have a meter to read the flow rate.
Yes.
Did you observe the change of that reading when the ball has been sucked up?
Suck up? The reason why we do this experiment by measuring the minimum flow rate it can flow is because if we want to measure the suck up flow rate, it is very difficult. Well, if we blow the air out, then the ball will go away. So it is very difficult to do this experiment.
Oh, okay. The other question is that the rotation that you observe when the funeral is conical one, then does the direction of the rotation keep the same all the time?
In the same way.
Did you observe the other way? Is there any preferred direction of rotation in your experiment?
Preferred?
I mean, the rotation will be all the same throughout the experiment, or
No.
sometimes in one way.
No, in our experiment, the rotation of the ball is all in the same way, the same direction.
Why is that?
Because if the impact first hit the ball, then the rotation will appear. So
Does that imply that your device is not spherical, symmetrical? Or,
yes.
okay, thank you.
I have a question for the recorder. So you talk about that the shape is one of the parameters,
Yes.
right? So where is that in your theoretical model?
Yes. So while we change the while we change the shape, the delta
No, I
X.
mean in that those formula, right?
Yes.
Which parameter describe
Delta
the
X.
shape?
Because the area between the funnel and the ball will be different in the conical shaped funnel and the spherical shaped funnel.
Other questions? Okay, thank you. And now 1 minute for jury to do the calculation of your score. Okay. Let's first check the scores for reporter. 8, 8, 8, 8, 7. Next is the score for the opponent. 7, 7, 8, 6, 6. Finally, the score for the reviewer. 6, 4, 4, 3, 5. Okay, this concludes the second fight. And we will be back on 35 at 10 o'clock. All teams, please change your seats.
你去拿我蓝笔吧。好，换下上去。
温下去了。
他们对牌怎么？你刚刚自己有看到自己对牌吗？ have reporter Wu Hongru, opponent Liu Weichen, reviewer Sun Jiangxi. The topic of this fight is Hurricane Ball. Okay, reporter, please make a presentation.
Hi everyone, my name is Wu Hongru from MDHS 18. Today I'm going to talk about my topic, number 6, Hurricane Ball. And this is our outline. First, I will introduce my problem statement and our theory. Third, our experiment and results. And finally, our conclusion. Here is the problem statement. In this problem, we have to spin the hurricane ball in by hand, and we will blow air on it, and it will spin incredibly high frequency. And this is our experimental video. And here you can see there is two rotations in the ball. First is the spinning. Because spinning is the if the symmetric, this is the spinning axis here. So the spinning means rotate like this. And second, we define the second is revolution. Its axis is here. So revolution means this way rotate. Okay, and through our video, we can see that if we rotate the hurricane ball, and it will slide on the table first, and it will stand up in our previous video. So, why do the hurricane ball stand up at first? Okay, now, because the sliding, and before at the sliding, A and B is touch the ground, so it haven't filled up. So, we assume that the sliding is slide into the page. So here will be two friction is out of the page. So they will cause a net out to the left. Okay. And this will cause the initial momentum downward will be this way change. So to adjust this angular momentum, the ball has to revolution like this. So they will have this direction. So the ball tilts up. And this is our snapshot to the ball. Here we define a coordinate system. First is the E1. E1 axis is the revolution axis. And E2 is out of the page. It's like this. And E3 is the spinning axis. And when it is revolution, there will be a angular velocity phi dot along the perpendicular. And there also be a angular speed psi dot, and it's along the spinning axis. And it's E3. So we have the total angular velocity here. And the rotational kinetic energy will be this. And here, I1 means the inertia when it is rotates to the E1 direction. And I2 means rotates in the E2 direction. And I3 means it rotates in E3 direction. Here, we want to talk about the steady situation, which means the theta dot is 0. In this case, phi dot and psi dot will be the same. We call it omega. its magnitude is omega. So our rotational kinetic energy will be like this. And we use Lagrangian approaches here. Our Lagrangian approach is here. And because delta dot is 0, so the second is disappeared. So we have the first direction of the kinetic energy, rotational kinetic energy here, and the third is here, and we minus the potential energy. And this is the Lagrangian approach. And because delta dot is 0, so we differentiate it by theta, we'll get 0. And after this differentiated, we'll get this result. Okay, and in hurricane balls, I1 is here and I3 is here. So our rotational kinetic energy will be like this. So Lagrangian approach will be like this. And we differentiate theta, and this is our final result. It's about the theta and omega. And we do 4 experiments. First experiment is to find out the relationship between spinning and revolution. And this is our chart. We can see that spinning and revolution angular velocity is almost the same in the time scale wise. And in this case we didn't blow air on it because we just want to find the spinning and revolution relationship. And this is experiment 2. We want to find out the relationship between spinning and revolution. And this is our video. Okay, next page. The difference between these 2 experiments is the first we use different table. First is glass, and the second is the laboratory tables in laboratory tables. And in these 2 situations, we can see spinning and revolution is the same. It's almost the same. So our assumption is right. And experiment 3. And because the former experiment, the revolution angular velocity is equal to spinning angular velocity. So we did this assumption in our experiment 3. And we use glass balls whose radius is here. And this experiment's idea is to find out the relationship between the revolution angular velocity and the angle between the perpendicular. And this is our data. And this is the theoretical curve. And our data is fit this curve. And our angle use radian, and angular velocity is radian per second. And this is our experiment 4. This experiment different from the third is we use iron balls whose radius is here. So we change the radius and we'll get a different result. Here is our theoretical curve, and the green point is our data. And we can see our data is almost fits our curve. And here is my conclusion. We use hand to create a revolution. So omega revolution is bigger than omega spinning. And we assume that omega spinning is 0 at first. So the friction on the table will start the spinning. Okay, and in experiment 3 and 4, we did blow air on it. So you can see the angular velocity didn't change with time because we use a stable flow. And when blowing air, omega r is bigger than omega s because the air is actually accelerates the revolution, and it will spin. The friction will appear again. So it was being faster to catch up the omega r. Omega s will be bigger to catch up the omega r. And when the first, and if the omega s catch up the omega r, which means the connecting friction should disappear. So it will be the poorly rotate. And this will cause very less energy loss. So this is why we think the hurricane ball can spin incredibly high, incredibly fast. Okay, and when ball sliding on a table, we have more energy loss. In experiment 1 and 2, we didn't blow on it. So as the time goes by, the angle will be bigger, and finally our hurricane balls will touch the ground, and this makes our angular velocity decrease very sharply. And this is our report. Thank you.
Okay. Opponent, please ask question.
And can you repeat your experiments the ball? I want to see your experiments this time. Yeah.
Here, this is, we don't blow it.
And can you explain again your theory?
Our theory.
Yes.
Okay. Okay. First, we'll have our rotational angular velocity, revolution angular velocity, phi dot, in the perpendicular. So theta here, we want it to along the E1, so we plus psi theta, and it will along the E1. Yes. So we have phi dot psi theta in E1 direction. And theta dot means the angle that it held up, so it will also have an angular velocity. So, but it is along the E2. But
The weight will affect this system.
weight, no, because in our final results, we can see there is not mass in here, so the mass won't affect.
Stop. Sorry. Time stop. We have 3 minutes for preparation. Okay. Please.
And this problem is how the two balls when air flowing and it will keep spinning and I think it has a very data is very good and it's easy it's bigger but I think where is your when you use the hair dryer and where is your video? Yeah, and that's. And can you catch the can you explain again this?
Okay, I think our data isn't fit like the 14 page, but I think it's still reasonable because this is the iron ball we use. This data is the iron ball data, and because the iron ball data is the iron ball's radius is little, is more little, so the frequency will be bigger. So if it is bigger, the theta we measure will be very close. So you can see here is almost a line, and this is angle.
Okay, and I have a main question is, you say the weight will not affect it, but
Yes.
Have you do this experiment to the panel? Because I think the friction is the main reason, and where is the reason? It's come from weight and a vector. A vector. Yeah.
Main vector means
What?
vector. So can you ask your question again?
Oh, okay. Wait a minute. Because the speed and weight is the vision main reason, yes.
Oh, so you
Right?
think
But you say the weight no affect this system.
yeah.
Why?
Okay. Here we use Lagrangian approach. In Lagrangian approach, we don't have to calculate the friction on the ball because it's the kinetic energy minus the potential energy, and the friction here is stable. In steady situation is the static friction. Yeah, so it won't affect the energy in here. You know. because it's the static friction.
I think, but it's not, but it's not no effect on this system, yeah? Right? I said the weight. The weight is
The weight will be in here in the inertia.
yeah. Oh, I know.
Yeah.
I know that. Okay.
And in our capacitor, the mass will be will disappear because here, mass.
And how to flow on a sand path? Because your ball is spinning, and but how to flow on a sand path? Because your
And here is our video. Sorry, the computer has some problems, so we can't play it when my report. Here, in fact, we use wind gun, and you can see we press the wind gun, and the wind gun will flow a steady flow, and the flow will accelerate this hurricane ball, and this is the slow motion. So we can check the ball.
Okay.
This is our setup of our experiment for in iron door, and we use wind gun.
And thank you very much.
Are you done?
Yeah.
Okay. Time's up. We move on to next stage. Opponent, please summarize the discussion.
And I think I'm very clear how what did you say, and I think the component is very accurate. First, the video is not very good, and our parameter is maybe they have a lot of parameters. So I think it's very clear to it's very good to know what is a yeah. Thank you very much. I'm finished.
Thank both the reporter and the opponent. I have a good question for the reporter that will the ball just rotate at a certain place or it will move on the surface?
We use the certain. In our video, you can see it sometimes will fix. No, yes, it sometimes will move, but it sometimes will fix. So our data is from the fixed way. It's the free situation.
Okay. To the opponent, do you think the ball moves on the surface will affect the result?
Yeah.
Yes. Okay. Then the report thinks that the inclination of the ball will reach to a maximum value.
Yes, of course. Because of here, if our omega is infinitely big, our cosine theta will be by 0.4. So we can calculate the theta is about 60 more degrees.
Okay, then the opponent, do you think the inclination angle will reach to a maximum value? you're good with the report. Okay, and then the report thinks that the friction between the surface and the ball will affect the result.
No.
No, the friction between the surface and the balls.
Yes, because our Lagrangian approach didn't consider the friction.
But you think that the friction between them will affect the result, right?
Yeah. Okay.
The friction between the surface and the balls will affect the result, right?
Very little because it's the static friction.
Okay. And to the opponent, do you think the surface between the friction between the surface and the ball will affect the result? Yeah. Okay. And then to both the opponent and the reporter, what do you think is the main factor affecting this phenomenon? The force that the main factor affecting this phenomenon. What do you think? The reporter first.
Okay. I think the ball will initially is on the table, but if we rotate it, at first it will tilt up, and I think that the main idea of the tilt up is because the kinetic friction at first.
The kinetic friction between the surface and ball, right?
Yes, at first.
Okay, and the opponent. Oh, that's okay. And what? Okay, thank you.
Okay. Okay. Thumbs up. Ready?
Yes. Honorable jury and fellow debaters, I'm the reviewer of Clinic Excelsior, and today I'm reviewing the question number 6, curtain balls. Here's the problem statement states that the balls will rotate at an incredibly high frequency and first spinning them by hand and then blowing on them and investigate this phenomenon. And here's the reporter's outline. He gave an observation video and he did a good job on explaining why the balls stand up and in the theory. And he had a good theory model, but he told us about the angular velocity and rotational kinetic friction, but there's no theory line in it. And the experiment is that the relation between two spinning and the revolution, but I think he could have been improved that these type of parameters. And the discussion, he told us about the angular velocity of the balls, but he has no no videos in it. And the conclusion is that he compared the theory between the theory and the experiments. And this is the opponent pros and cons. The opponent did a good job on figuring out the weakness of the reporter, and he helped us to understand the theory more clearly by asking the reporter. But the cons is that he's a little bit lack of time controlling, and he didn't discuss a lot about the most important parameter. And I think he could have improved that. He didn't listen carefully to the reporter's presentation. And this is the first discussion is that the opponent asks about how did the phenomenon happen. The reporter answered the opponent by explaining the theory again. But the reviewer believes that the friction gives the torque for the balls to rotate and spin, and the vertical component will give the vertical component of the torque will let the ball rise up. And next discussion is that the opponent said that do you think the wave won't affect the result? The reporter answered him by showing the theory on page 7, which include the cosine theta part, and the reviewer agrees with the reporter that the wave didn't calculate it in the formula, so the wave will not affect the inclination angle of the hurricane balls. And next is the opponent asks that how to flow on the same place, how to control the balls rotating at a certain place. The reporter says that wouldn't run slow motion to track the certain place, but I disagree with the reporter since that the ball will still slide on the surface. And I asked about this is the Q&A I asked about the reporter and the opponent about maximum inclination angle move on the surface and the main factor affecting this phenomenon and the friction. And this is the point is the reporter didn't show us the definition of high frequency, which the problem statement required, and the formation of the torque. He didn't explain it clearly, and why the error appeared in the result since it didn't matches with the theory line. And my conclusion is that vertical component of the torque is the inclination angle for the balls to rise up, and the maximum it will reach to a maximum inclination angle, which I agree with the reporter. And the ball will reach to a terminal speed while rotating, and the normal balls give the torque to rise up. And thank you. This is the end of my presentation.
Okay. Thank you. Reporter, please make your conclusion.
Okay, here's my conclusion. Through this chart, you can see that this part is the angular velocity is sharply decreased. It means because when it is the 9 seconds, the two balls touch the ground. Touch the ground means the kinetic friction appears. So kinetic friction will cause a lot of energy loss. So we can see the angular velocity have a sharp decrease. And here, and this long time, the balls didn't, one of the balls touched the ground, so it decreased very smoothly. Okay, and I have another important thing is through here we can see I1 plus I sin will affect the cosine theta, which means if I1 is much bigger than I3, which means the distance here is larger than the distance here, like a rod. A rod is very long, but it's very thin. So this will be very big, because the cosine theta will be very small, which means theta is nearly the 90 degrees. If it is the 90 degrees, the ball won't stand up. So we think this hurricane ball can stand up and for a long time is because the I1 plus I3 is not very big. So the theta will very so the tilt up angle will be very top. Thank you.
Okay. Now is the question time from the jury. Any questions? Yes.
Question for all of you, starting from the reporter. If we color these two balls with different color, if we paint with different color for these two balls, can you predict which ball will stand up? What determines which one to right?
I think here. This is the first situation, and if the sliding is into the page, the friction will outside the page, right? So it will cause a neck torque. You can see this is our axis. So the torque direction is here. This causes the here direction, and it have a initial revolution angular velocity. It's downward if it is clockwise revolution. And this will cause a change of the angular momentum. So the angular momentum should be here, should be like this direction. So this ball will tilt up. So they can have these directions, revolution, and will have these directions, angular momentum. Yes.
So what's the function of blowing this system with air?
We blow it because we want to accelerate it, and we can get different omega, and we can get more data and see if it fits our theory.
Okay, thank you. Ed, what's the opinion of yours? So you, what's your answer? I'm just trying to figure out whether you can predict which one would rise.
I agree with what the reporter said about the angular momentum.
So it keep growing and growing.
The usage of the flow rate is to accelerate the ball, so we can have the high frequency as the purpose they require. Yes.
So at some frequency, then you will have the condition to rise up. Is that what you say?
Yes.
Thank you.
Thank you.
Opponent, do you want to answer the question?
What? I can why it can it's just spinning, but why it will why the ball will get
Okay. Yeah.
Okay.
Thank you.
Thank you. Other question from the jury? I have one question. The reviewer mentioned in her summary that you didn't define what do you mean by incredibly high frequency.
Oh well,
What do you compare with?
with a rod. Like my conclusion. I said the rod can't stand up at very fast angular velocity. And I think 100 more radian per second is very fast. If you divide it by 2 pi, it will be 10 more rounds per second it rotates, in revolution,
Let's compare it with what?
with a rod.
The rod. Okay. Other questions from jury? I have one again for the opponent. Hello? Hello? If I now replace the balls by glass balls,
yeah.
do you think it will rotate faster or slower?
If you said
Here he is using steel, I think, right? Your ball is made of steel.
We do 2 experiments, experiment 3 and 4. 3 is in glass and 4 is iron.
Okay, iron and glass.
you say which is faster,
Yes.
which is first.
Of the same size.
But it is being it's yeah
can know how many yes, you can know how many times is
Time's up, sorry. Okay.
Okay.
Yeah, the jury will calculate your scores. Okay? Jury will give you the scores. First, for the reporter, 7, 6, 6, 7, 7. Then for the permanent, 5, 4, 4, 4, 4. Finally, for the reviewer, 8, 7, 8, 8, 8. Okay, so this concludes the morning session.